In this video segment, we're going to talk to you about how we mass in quartz and how we add carrier. We mass in quartz and we add carrier because we're doing an isotope dilution experiment. We need to know the mass of quartz because all of our measurements are referenced to atoms per gram of quartz. And we need to add carrier because there's very little native beryllium-9 in quartz. And although there is some aluminum-27 in quartz, the stable isotope of aluminum, there's often not enough for our process. So we start with clean quartz, that is quartz that's typically under 100 parts per million of impurities, and we usually use between 10 and 40 grams of that quartz. We add to that quartz carriers, and carriers are predominantly the isotope beryllium-9, the stable isotope of beryllium, and the isotope aluminum-27, the stable isotope of aluminum. We add carrier to do what's called an isotope dilution experiment. So we mass in a certain number of grams of quartz, and we measure that mass using a balance. And then we add a certain amount of carrier, in this case beryllium-9, to that quartz. And the reason for that is so that we can move the beryllium through the chemical processes. There's so little beryllium-9 native to quartz. We add that carrier, we also mass that. Since we know the mass of the carrier and we know the mass of the quartz, we can then go to the accelerator mass spectrometer that's pictured here and measure the beryllium isotope ratio. So we're measuring the 10 beryllium to 9 beryllium isotope ratio. If you multiply through with the number of atoms of beryllium-9 that we've added, because we know the mass, and you divide by the grams of quartz, we can calculate then in the end, after all these measurements, the atoms of beryllium-10 per gram of quartz. And that's the value that comes out of our lab and AMS work, and that's what's used to interpret the geology of the field setting. So we have a particular equipment setup that we use, and we're going to walk you through those various pieces now. We start with Teflon bottles. Each of those Teflon bottles has a label on it, and each of those labels tells us which sample is going to go in the bottle. We have the samples of quartz in test tubes. These are in 50 ml test tubes. They are labeled, and they have the concentration of various impurities in the quartz on those tubes. We have an anti-static device. It's a U-shaped device that has an ion field around it that helps reduce the static on the Teflon bottles and on the quartz so that we can make an accurate measurement of the weight. We have a balanced check weight record, and that means every time we sit down to weigh samples, we use a series of calibrated weights that we know the mass of to make sure that our balance is performing properly, and we write down those values every time we sit down to mass in a batch of samples. We have a balance that reads out to 4 places. The purpose of this is so we know exactly how much quartz we have added to each sample. We have a marble balance table, happens to come from Proctor, Vermont, weighs about 1,000 pounds, and that helps reduce any vibration so that we can get a good measurement on the balance. We have a DI wash bottle that we use to wash down the sides of our bottle and to dampen the quartz. We have several carrier pipettes. This is the aluminum-27 carrier pipette. It's a variable pipette, so we can make a calculation of how much aluminum carrier we need to add to get to a total of about 2,000 micrograms of aluminum in each sample. That gives us plenty to prepare at least 1 and sometimes 2 cathodes from each sample for measurement on the AMS. We have a beryllium-9 carrier pipette, and this is a really fun pipette to use. It's electronic, it has a reservoir, and so each time we push that button on the top, we can dispense about 250 micrograms of beryllium-9 into the sample. And of course, we do that by mass, and we read the mass of that addition.
Okay, the beryllium mass is 0.8337.
We have a quality control standard that we add to each batch. We run it as a sample in each batch. And that's a way to check that the accelerator mass spectrometer is giving us the results that we would expect and to check if we have any contamination. As we do this weighing in, it usually takes either 2 or 3 people. One person will be sitting at the balance. This is Christine at the balance here from Northern Arizona. She's adding in samples, and in the background are 2 other students, one of whom is watching, the other of whom is actually entering data on a computer as we mass in. So we collect all those mass data as we add carrier and as we add samples.
0.5790.
We have specific data collection sheets into which we enter these data. They're Excel spreadsheets. And here's one of those data sheets. It's got a sample ID. It's got the position on the rack. We use letters to denote that position. We have the mass of the bottle in the lid, and we have the mass of the sample that we've added, as well as the mass of any carriers that we've added on here. Here's the repeating pipette in action, and you can see that everybody who does this is gloved. They're wearing goggles because there's some weak acids in with these samples. And we add that carrier, the beryllium carrier, through the top of the balance, carefully making sure that all of it ends up in the bottle and not on the balance. Here's that bottle rack. You can see each of the Teflon bottles held within acrylic and with a Teflon surround on there. The other purpose of this rack that you'll see in one of the next videos is that it keeps the bottles warm as they're sitting on a hot plate, which increases the speed and the uniformity of the digestion with the HF. We have a little anti-static shield on that valve. It's a sleeve, and it's just made of metal, and it bleeds static off the Teflon bottles. In the middle of winter, in labs that get really dry, there can be an awful lot of static. Here's a close-up on that Beryllium Carrier and the automatic repeater pipette. We make our own Beryllium Carrier for most samples. For very low-level samples, we make it out of beryl. For other samples, we have a 10,000 ppm spec standard that has a very low beryllium 9-10 ratio, and we've diluted up many liters of that, and that's what we use for most samples that go through the lab. The aluminum carrier is a standard specs ICP standard, which gives us quite low ratios. It's mostly aluminum 27. So the goal of this part of the procedure, massing in quartz and adding carrier, is to do an isotope dilution experiment. And by that, what we mean is we know the mass of the quartz, we know how many grams of quartz we've put in, we measure that precisely, and we add known quantities, also measured precisely by mass, of the stable isotope of beryllium, beryllium 9, and if needed, more of the stable isotope of aluminum, aluminum 27, although often there's plenty in the quartz. We do this in a way where we have everything measured precisely, we've reduced the static, and we've recorded these data, because without them, we can't measure how much beryllium 10 or aluminum 26 is in an aliquot of quartz. From here, we're going to move on to adding acid and dissolving this quartz, and then through the chemical process to purify it.